Hello and welcome to this course on CSCI 3104 algorithms. What are algorithms? So in this course we are going to study algorithms, and what are they? An algorithm is a computational procedure. Now what does a computational procedure mean? So here we can think of an algorithm as a box which has some inputs and produces an output. Alright, so that doesn't say much, does it? So for example, what would be an example of an algorithm? For example, let us talk about some, the first example would be algorithm to multiply two numbers, or even better, algorithm to add two numbers. Okay. Now what's an algorithm to multiply two numbers? So for example, suppose I gave you an input. The input would be two numbers, n comma m, and the output must be their product, m times n. Okay, so this is an example of the specification. So n and m are integers, and output is the product of m and n. All right. Now as an example or as an instance, so whenever we plug in values for the input, we call it an instance of the problem. So what's an instance of this problem? So let us take n equals 121 and m equals 234. Fond memories of grade school, all right? And what is the algorithm? The algorithm is going to be a step-by-step procedure to perform this kind of multiplication, all right? Now, how does this algorithm work? Well, I'm not going to go into the details of grade school multiplication. And in fact, it's coming up. We are actually going to study multiplication in this class, okay? But let's recall what we did in grade school. So we know how to multiply things by a digit. So we take the first digit, 4, and then we run through the multiplicand, all right? So now we get 484. Then we take the second digit, but now we shift one place, okay? Multiply by 3, now we get 363, and formally a 0 there, all right? Then we take the third digit, we get 242. I'm going to stop writing the zeros, okay? Just like we did in grade school, and now you add 4 plus 0 is 4, gives a carryover of 1, 1 plus 8 is 9, plus 3 is 12, carryover of 1, 5 plus 6, 11, plus 2, 13, carryover of 1, 8, 2. Hopefully I did it right. I have no intention of going back to grade school and relearning this, but what you learned in grade school, the procedure, the step-by-step computing procedure in carrying this out is an algorithm, okay? So where does the term algorithm come from, all right? So algorithms are not a new subject. Algorithms are in fact a very, very ancient subject where cultures around the world discovered that they needed to compute, and to compute they needed procedures by which you could take things and run computations and come up with the answer. The earliest algorithms were kind of numerical algorithms, all right? Multiplying two numbers to find out their product, for example. And that was required because we needed to compute the area of a rectangular piece of land, and the only way we could do it is measure both the sides and multiply them, all right? Or people needed to predict when the next eclipse was going to come. So they needed to do these calculations to figure out when the next eclipse was coming, when the next full moon was coming, when the next tide was coming. So people had a lot of calculations, okay? And they needed algorithms to carry out these calculations. And the earliest kinds of algorithms that we know are, for example, the algorithms that Chinese mathematicians did to calculate on the abacus, all right? So for example, calculations using abacus, all right? Indian mathematicians, ancient Indian mathematicians, invented what we today call the place value number system. All right, and that was super important because not only did they invent the place value number system, they also invented the arithmetic algorithms to go around with it. Then there were Greek mathematicians who invented algorithms for calculating things like GCDs, Euclid's algorithm, remember? Finding if a number is prime, Eratosthenes' sieve. So there were plenty of algorithms to go around from the ancient world, all right? And there were people who are doing calendrical calculations. Okay, so algorithms have been around for a long time. And what we are learning is just modern algorithms, all right? Now, what is modern about these algorithms? So everything changed because of the invention of the modern computer. Okay, once we invented the computer, people started to want to calculate things in a systematic manner, all right? And because people wanted to calculate things in a systematic manner, modern algorithms was born, the study of algorithms. And in fact, one might be wondering, where does the word algorithm come from? I am never too sure, but it comes from the name of this great ancient mathematician, okay, Al-Khwarizmi, and he lived somewhere in ancient, what is today modern day Persia. It literally means the person who is coming from this place called Khwarizm, okay, and he wrote a very famous book on solving equations, on doing arithmetic, and this was where the source of Arabic numerals come in, okay, even though they were invented by Indian mathematicians and passed on to the Arab traders who came to trade, all right. And so we had Arabic numerals, were so-called Arabic numerals in the West. And because the book that Al-Khwarizmi wrote was translated into Latin and studied by Western scholars, it became so popular that the term that we use for algorithms comes from his name, or more from the town that he came from, all right? And so we have modern algorithms, which were born because we were really interested in computing, all right? And in fact, a very interesting history is a lot of mathematicians came up with algorithms, all right? A lot of mathematicians used to come up with algorithms, algorithms for solving equations, algorithms for computing the root of a polynomial. So there were lots of algorithms that were invented from the ancient times up to the pre-computing era in human history. Unfortunately, what happened to all those algorithms is people in mathematics thought about algorithms often as just an afterthought or not worth publishing. In fact, there are plenty of examples of very important algorithms that we use today that were not even deemed as worth publishing by their inventors. Okay, there are plenty of algorithms in history where people said, oh, this is just an algorithm. The most important thing is the theorem, all right? But with the advent of computers, all of that changed because now there was a demand for efficient algorithms, things that we could compute. We wanted to multiply 1,000-digit numbers or 100,000-digit numbers. We wanted to find out if a million-digit number was a prime. To do all of that, you needed a computer because human brains could not really do that kind of calculation in any finite amount of time without making a mistake. So we wanted computers. Once computers came, people quickly realized that they needed to study algorithms as a first-class field of study by itself. Okay, so it's a very exciting area in computer science that borrows a lot from mathematics, but it's uniquely a computer science discipline because algorithms are meant to be implemented on a computer. These are abstract recipes for carrying out computation that need to be invented on a computer. Okay, so in this regard, there are two very important steps forward that happen. The first step forward, in my opinion, and this is all subjective, mind you, different computer scientists have different opinions. The first person whose name you need to know in this context is Alan Turing. Okay, and if we look at this term computational procedure, there was no definition of a computational procedure. What defines a computational procedure? What is a computer? Okay, so Turing came up in the 1930s. Turing came up with a model of computation. Okay, and this model of computation is exactly the model of computation that works on your machine. Okay, and in fact, there is a thesis called the Church-Turing thesis, which says that any computer that can be physically realized in our world using the laws of physics, using silicon, using electronics, any computer that can be realized is exactly as powerful as Turing machine, okay, which is what Turing called his model of computation. It's called a Turing machine, all right? And once Turing defined a Turing machine, it became very clear to us what is a computational procedure. Even though in this class, I am not going to teach you about Turing machines, it is still really, really important that there is a definition of what it means for a computational procedure. Okay? And it's a beautiful definition. If you ever take a course on theory of computation, we will go through this definition in great detail. But for this class, we will not assume that you know this definition, but we will kind of somehow be wishy-washy about it. All right? And then, so just, we kind of don't attack this problem in great detail, but know that there is a computational procedure and it is well defined. There is an ideal computational machine that does all the computations that we can describe in an algorithm, and that's called a Turing machine. Okay? If this is too abstract, don't worry. Another big name that I have to mention in this context is that of Don Knuth. All right? And Don Knuth, in my opinion, was very, very instrumental in the study of modern algorithms. He wrote this famous book called The Art of Computer Programming. Okay. Initially, Don wrote this, and he said he was going to publish 3 volumes that collects all the algorithms that people know about for most of the problems people care about. And now Don is still continuing to write this book. He's still alive. He's a professor at Stanford. He retired about 20 years ago. And I had the pleasure of actually knowing him when he was a professor and I was a student. All right? And he's now into volume 6 of this book and continuing. So, if you're interested in a good Christmas gift for the computer scientist in your family or the computer scientist you know, how about getting them The Art of Computer Programming? All right, but more seriously, I'm not here to sell this book, but this book is kind of the Bible. Okay, it has a lot of what algorithms are, but it's not a textbook. It's more of a reference book. It's more of a book that you keep in your shelf so that if you need to see what the best computational procedures are, algorithms are for a particular problem, let's say factoring a polynomial, then you open up the right chapter in Art of Computer Programming. Typically, volume 2 will have that. You open up the right chapter, and it gives you everything you need to know about factoring algorithms, circa 1990s. All right, so this is more of a survey. So we don't use this as a textbook. The textbook for this class is a very famous textbook. It's fondly known as CLRS by everyone who studies computer science. It's a textbook by Corman, Leisesen, Rivest, and now Stein. Okay, when I was a student, it used to be CLR. Now it's CLRS. And 20 years ago, when I learned algorithms for the first time, I studied from the same book. It's a good textbook. Okay, it's a good textbook, and it's also comprehensive. So you don't need to buy the 6 volumes of Art of Computer Programming. CLRS has a very, very good description and a very good exposition of most of the algorithms that you are ever likely to encounter. So in this class, we will do the classic thing and learn from CLRS. Okay? And there are some other books. So recently, I came across a very delightful book called Grokking Algorithms. And I have recommended this book as an optional textbook for you to download and read. And this is a very, very useful textbook. All right. So to summarize everything I've said so far, we are going to study algorithms in this class. An algorithm is a computational procedure or a computational recipe for solving a problem you're interested in. Algorithms have inputs, they compute, they provide outputs. For example, to multiply 2 numbers, the inputs are 2 numbers, the output should be their product. whenever you give inputs to whenever you plug in actual values to these inputs, you have what is called an instance of the problem. And once you have an instance of the problem, the algorithm runs in a mechanical manner. So there is no creativity when you run an algorithm. It's just a step-by-step blind procedure that just tells you imperatively how to do this. Once you have done, you get an answer, and that's the answer. Okay. Algorithms have been around for a long time. Algorithms are not by any means a modern invention. They have been passed from ancient human beings. They are kind of a legacy of our culture. Just like mathematics is, there is algorithms. People did not really pay attention to algorithms until the advent of computers. You need to know that the notion of a computational procedure, what constitutes a valid computation, was defined by Turing in the 1930s to lay the foundation for modern computer science through something called the Church-Turing thesis by Alonzo Church and Alan Turing. And there's a wonderful history here. You should look into Don Knuth's books, 6 volumes of the Art of Computer Programming, which really kicked off the study of algorithms as a serious discipline in computer science. Okay, so welcome back. So in this lecture, I'm going to talk about algorithms as a technology. Okay, I'm going to talk about how algorithms influence and interact with everything we do in our digital lives and even outside of our digital lives. All right, so every time you log on to Google to do an internet search, okay, so every time you log on to Google, you are actually relying on the power of rapid, highly efficient algorithms to find the web pages that are relevant for your search. So suppose I wanted to search for best Greek restaurants, okay, and I place this search in Google, let's say, which is a good search engine that we keep using a lot. All right, suppose we do that, then how does this work? In the back end, what are the algorithms that are brought to bear about to carry out the search for us, right? So there are many algorithms that have to be employed to fulfill this result. So what do we expect to see? We expect a page to pop up with a list of the best Greek restaurants with reviews. How many stars? And typically, they are not best Greek restaurants in Athens, Greece, or in or somewhere in the islands. They are the best Greek restaurants near us. Okay, so one of the things that happens is it knows your GPS location, the approximate location from which you are asking. So what Google can do is it builds up an index. And this index has been built beforehand. Okay, and in this index, which is more like a hash table, something we will learn, you have a bunch of GPS locations or geographical locations, and from there you map to various search terms. So one of those search terms would be Greek restaurants, and from that search term you have a list of locations. All right, and there is also a service where for each of these restaurants you map to reviews for this restaurant. All right, and therefore using this index, Google does a really fast search to find out based on your query. It knows your GPS location. It understands that you're looking for restaurants. So using your GPS location, it gets the restaurants. It then gets the Greek restaurants, and then it compiles the page and sends this back to you. And all of this needs to happen in milliseconds to seconds, or else you think it's too slow to load. All right. So this is an example of a bunch of algorithms that are in action to make all of this happen for you behind the scenes. Another example is if you are going to search for a route from address A to address B. And let's say you're doing it on your favorite app, Waze. All right. Let's say you're doing it on your Waze app. Well, nevertheless, what Waze has to do is it needs to know where address A is located on a physical map. It needs to know where address B is located on the physical map, and it solves for a shortest path. It solves for a shortest path problem, okay, and it does so. And not only a shortest path, it also computes some alternative paths, not just so that you have some idea of what the routes are. And it looks at each of the paths. It looks at the current traffic information, and it estimates how long will you take to reach from A to B. All right. So all of these rely on patching together a bunch of algorithms, okay, and that's super important. Where else are algorithms at play? All right, every time you fly and you go to an airport, there are a lot of algorithms that are coming into play from the moment you board the airport on your gate, airplane on your gate, until takeoff and even after takeoff. What are these kinds of algorithms? So for example, in any airport, you have a resource constraint. You have a few runways or you have a few taxiways for planes to land, all right? And you have lots of planes that are waiting to land, all right? So an air traffic manager needs to schedule these planes who are waiting to land. So this is not usually automated. This is often done manually, but once they are landed, then each plane needs to be assigned to a gate. Okay, so this assignments of planes to gates is going to be a hard problem. So it's an example of an assignment problem. Okay, for which we will look at efficient algorithms. The idea of assigning scheduling planes that are landing onto the taxiway is an example of a scheduling problem for which there are efficient algorithms. And they come up in a lot of contexts: scheduling problem, assignment problem, and then, for example, once you are ready to take off, there is a scheduling problem where the runway needs to be scheduled for all the planes that are waiting to take off from the runway. All right, so that's an example of a scheduling problem. All right, so every time you go to the airport, you see there is a lot of logistics that are going on in the background, which are being handled by algorithms. I don't even want to start about how your bags that you check in are going to be handled so that they reach the plane on which you are flying. All right, so that's a whole logistical nightmare. There are tons of algorithms. I don't need to tell you, for example, that every time you go to a gate and you are about to board an airplane, there is an airplane that comes to your gate and takes you to your destination. Okay, now where is this airplane coming from? The airline doesn't reserve an airplane to your route. Usually it doesn't work that way. Usually what happens is the airline tries to schedule the airplanes that it has available to the routes that it needs to fly. Okay, and sometimes if things get delayed, you might find a different airplane is brought into service, or if an airplane breaks down, if there is a technical fault in your airplane, then a different plane is brought to take you from A to B. And those kinds of problems are called vehicle routing problems or vehicle assignment problems. Okay, so there's a ton of logistic problems that happen every time you operate on an you go to an airport and you would like to go from destination A to destination B. Another example of algorithms come in would be, for example, suppose you send a package through FedEx. All right. Now FedEx has algorithms that are going to schedule your package on the right plane or the right transport to get from A to B. When you get from A to B, then there is a truck that has a bunch of packages that need to be delivered to a bunch of addresses, and the truck needs to come back to the same place it started, to the depot. All right, and this is called the traveling salesperson problem. Or TSP. TSP is a very, very difficult problem to solve. If you can solve it efficiently, you can end up saving companies like FedEx a ton of money. All right, if any efficiency gains you can make in solving TSP problems will mean a lot of money to a lot of people. So this is an example of an algorithm that can make a huge impact on people. Another example of where algorithms get used are places like you will find them in all the odd places. For example, if you are a medical student, okay, and you are looking for a residency, all right, so there is something called a National Residency Match Program, okay, which assigns medical students to the residencies that they would like to go to, all right, and this is based on an algorithm called the stable marriage algorithm, okay, and the people who invented this algorithm won the Nobel Prize. Okay, so they were from economics, and because of this invention of algorithm for efficient allocation of resources, efficient allocation of resources, they won the Nobel Prize. Okay, who won the Nobel Prize? I think it was Gale and Shapley. I may not be sure who the other person was. There was one more person who actually ended up passing away before the Nobel could be awarded, but the prize, I think, was awarded to two people, Gale and Shapley. They're economists, and they won the algorithm for designing this algorithm called the stable marriage algorithm. And they came up with a very flippant version of this problem of assigning men who would like to go on a date with women, all right. But it turned out to be really useful. It's used for assigning residents, people who have finished medical training, to hospitals that are looking for trainees to staff positions. And there, residents want to have a job, right? No resident wants to be left without the opportunity to train. And valuable training spots in hospitals need to be filled, and people need to be treated. So with this program, you get efficiency. You get residents who are looking for a job, get a job. Hospitals that have a vacancy, get a vacancy. And this is a really great algorithm. It's also been used for matching kidney donors to kidney patients. All right, so there is a ton of places in our life where algorithms come in and help us be efficient, help us avoid wastage, help schedule things, help assign jobs to people. So algorithms are really all around us. So next time you're using a computer application, or you're in the airport, or you get a package delivered by FedEx, I would invite you to imagine what kinds of algorithms were employed to make sure that the package reached you, or to make sure that you actually got on a plane and you took off safely to your destination. And I don't want to even mention the algorithms for routing planes to make sure that despite wind conditions, they take a fuel efficient path to go from whatever your source is to whatever your destination is. So algorithms are all around us, and they are really important in helping us run our society. We use them every single day, whether you realize it or not. Okay. So with that, I'm going to, in the next lecture, talk a little bit about algorithms in this class, talk about pseudocode, and introduce your first algorithm for sorting. See you in the next lecture.